All right, so we've been looking at searching, we've been looking at sorting, and now we're going to look at a third very common problem in computer science, and um, it's called hashing, and it's interesting and it's valuable because it relates directly to the dictionary object that we've used quite often in Python. So a Python's dictionary object allows us to look up values by a specific key. So we know that the dictionary was a key value um, store. It was a key value, stored key value pairs. Um, Lookup sounds a lot like search. You can imagine trying to implement a dictionary, and you could sort of have like a list of maybe tuples, and you could. The first entry in each tuple was the key, and the second entry in each tuple was the value. And you could simply search through the list for the tuple with the key that you were looking for. And we know how to search, right? And if in fact if we knew that um, if the key was orderable, which it probably is, a float is orderable, an int, a string, most things are orderable, comparable. We could sort them, and we should be able to look them up using some sort of a binary search. So we should be able to get log n, which is pretty good speed. However, if you actually run timing on the Python dictionary object and you add enough values to get a meaningful result, you'll see that somehow Python seems to get more close to a constant lookup, meaning that the amount of time it takes to retrieve a piece of data out of a dictionary um, isn't affected by the number of things in the dictionary nearly as much as you might believe it should be, at least if you were thinking about log n. And Python's not special here. Many other languages have dictionaries or dictionary similar objects that behave like them, and they can get close to constant time. So the question is, how exactly is this possible? So first off, the key lies in a kind of a subtle distinction between the word lookup and search. When a computer scientist says lookup, they mean something different than search. You search for something when you essentially don't have a real good idea of where it should be. Um, you don't have any reason to believe it should be in a particular place. When we say lookup, we we're sort of implying that we already know ahead of time roughly where it is. So you go look up a value. And so that's sort of if you already know kind of where something is, it's not really a search, right? And certainly now you can start to think, oh, well, wait a second. If the dictionary somehow already knows where the key value pair is in memory and inside some sort of a list, well, then it stands to reason that the search time wouldn't be that much. So the question is, well, how would it know ahead of time where a particular key value is supposed to be in a list if what you're asking it to do is go find a key? So to give you an idea of how this is done, it's actually a very straightforward and simple process. Let's say we had a list. We had to have or store a list of everybody in the United States. A good key for that would be social security number. Everybody's got a different social security number. So let's assume we wanted to find people by their social security number. There's about 314 million people in the United States. So we'd have a very long list, right? We'd have a list of maybe tuples where the first entry in the tuple was the social security number and the second entry was all the information about a person. Who knows what else we'd be trying to store. So what we could do is we could sort by social security number, but realize that just sorting by social security number doesn't really tell you what index to go find the person at. If your social security number is, 157 932348, right? Well, that doesn't necessarily mean that you're going to be at index, whatever that number is, 157 million or 15 million, something like that. Because there's a lot less people than there are social security numbers. There's more possible social security numbers than there are people, so that it's not going to be at an index necessarily that corresponds to the actual social security number. So this would be very much a search. If you had a big long list, you'd have to search. You could do a binary search, but it's still a search. So how do we do lookup? What if instead we, and by the way, we're essentially proposing that we're going to sacrifice memory for speed. But what if instead we decided that we would always create a list with 1 billion entries? All right, so a social security number requires all 9 of these digits. So this would give us, if we had 1 billion entries, we'd have 000, zeros across all the way to 999,999,999. So if we committed to having a list of 1 billion entries, then actually we could designate, index 514439212. We could designate it that that index only holds, if this person exists, the person with this social security number. Right? So there's a difference here. In a list of every social security number being used, you'd have a list of around 314 million. In a lookup table, and this is what we're describing, a lookup table, we have many more entries, but lots of these entries are going to be missing. They're going to be none, but they're still going to exist. It's going to be a list with a literal none value stored for the people or social security numbers which are not currently assigned to a specific person. So now the value of this, we're certainly sacrificing memory, but the value of this is that when looking up this person by their social security number, there's no need to search. We go directly to this index. There's no question about where that person's information would be found. That's a true lookup table. So the drawbacks, of course, is that we've got 1 billion indexes in our list. About 2/3 of them have none stored with them because their social security number isn't currently being used. That's obviously very wasteful. None requires memory, believe it or not. So you literally do need to have a list with memory allocated to all of these indexes, just to at least say none. The advantage, though, is that it's a trivial and very, very quick lookup. So this is a great thing to have. This is kind of problematic. We don't really want all of that wasted space. So what we do is we get a bit of a compromise. And compromise starts with the realization that we're using a very, very simple, straightforward key, the social security number. So social security number is really easy to turn into an integer. The reality is that there are many more possible social security numbers than are actually being used, and that's the underlying problem, right? There's more social security numbers available than actually used, so you have wasted space. So this is such a common problem that we've got data structures for this, and it's called a hash table. And the issue is that we very rarely use an unaltered key. So typically we wouldn't use an unaltered social security number. We would do something. We would transform the social security number by some function, by some method, which doesn't have to be overly complicated, but can, into an index. All right, so there's going to be a relationship between social security number and the index, meaning if I know the social security number, I can find the index where that value will be, but it's not going to be exactly the same. There's not a one-to-one relationship. So what we call this transformation is hashing. We hash the key. All right, so when we hash the key, it gives us an index into our lookup table. All right, so what does that do for us? It converts an input, all right, so social security number, for instance, into some output, an index, in a predictable manner, first off. So the same input's always going to create the same output. But the key property is that there are many of the same inputs mapped to the same output, or many different inputs mapped to the same output, meaning there are several social security numbers in this case that would actually go through our hashing function and map to the same exact index. And we're going to have to deal with that. We'll call them collisions, hashing collisions. So for instance, if the key is an integer, let's say it was a smaller integer, not a social security number. Let's say we chose as a hashing function, a transformation function, modulus of 10, meaning divide it by 10 and take the remainder. Well, if we did that, then if we had a key 2342, it would hash to the value 2. If we had a key 4317, it would hash to 7. And notice that the key value 9187 would also hash to 7, right? So we have a collision. But I also would point out that how many actual entries in the list do we really need? Well, if we're taking any number and we're modulusing it by 10, we only need 10 possible lists or places to put in our list. We only need 10 entries in our list, 0, 1, 2, 3, all the way up to 9. So that's a key insight, right? We're saving space. We only need enough space for each individual hash result, not each individual key. So a hash table works as follows. To store or find a key value pair, we take the key value. All right, so again, think back to social security number. We hash it. And the hashing function could be very simple. It could be a modulus operator. If the key is an integer, or we can easily turn the key into an integer, then we can hash it just with a modulus operator and it'll be fine. Then we go to our table at index hash, right? Not at index key, but at index hash, and that'll have the value. Each entry in the table is not just a simple value though, because recognize that if we go back here, we're clearly going to have multiple things, multiple values whose key hashes to the same output, right? So in this case, the index 7 would need to hold both of these key value pairs, both keys. So each entry in our table is actually not a single item, but it's a list, and typically we call them a bucket. It's just a list containing k values, and k just means it's the number of keys that collided at that particular location in the hash table. So k is the number of keys stored in a table that hash to the same exact value. Right? And the value, a good hashing function minimizes the number of collisions, but it's not going to eliminate them. The only hashing functions that can eliminate them are hashing functions that have unique input and outputs, which is not really a hashing function. So why does this all work well? Well, the set of all possible keys is larger than the set of all keys, right? Of all used keys. That was the case with if we just use social security numbers, right? The set of all possible social security numbers is much, much larger than the set of used social security numbers, which means we're going to waste a lot of space because we were trying to allocate entries in a list for every key. But the set of all possible hashes is going to be less, right, than the number of the used keys. All right, so that's key. Not too much less because we don't want too many collisions, and we'll have to think about, well, what does too many really mean? But if it's reasonably considered, if it's a reasonable hashing function, to find the right bucket is going to cost us no time at all. Right? We're just going to do a modulus operator or something similar. So we're going to have constant time to find the right bucket. Then to search the bucket, because the buckets have a number of collisions in it, it would be order OK. And I'm instead of writing ON, I'm writing OK, only because I'm kind of differentiating between this. N would be the number of possible values in the hash table. K is a much smaller value. K is the number of collisions at a specific hash index. As long as the hash table does its job well, K is going to be substantially less than N, dramatically less than N. And if we do that well, then we've got an algorithm that can allow us to look things up very, very quickly. So kind of going back to social security numbers as an example here, a good hashing function might take that social security number and take a modulus of 10,000. So if you think about it, that would be the last 4 digits, right? If we ran a social security number through a hash function that did a modulus of 10,000, we would get all the values 000 through 9999. So we'd have to have a table with 10,000 entries in it. And certainly we could possibly have many, many people hashing to the exact same entry, this exact same bucket, right? There's a lot of people out there. There's 314 million people out there with social security numbers. There's going to be a lot of them whose last 4 digits match, potentially 10,000 of them, given the number of, with social security number has 3 digits, then 2, and then the last 4. So we could have, actually, this is an underestimate. Really, I guess we would have 100,000 because we'd have 99999. So we could have theoretically 100,000 people mapping to the same bucket based on 100,000 people having the same last four digits. It's probably going to have it's probably going to be much less than that. That's just a maximum. But on average, though, we're having a lookup speed that has been increased by a factor of 100,000 times, right? We have an O(n) divided by 100,000 rather than 10,000 or a billion. Right? So we could do much better, of course, if we had more buckets, right? So if we were willing to maybe do a mod by, 100,000 instead, well, then we have a max of 10,000. Let me remove the right zero there. Then we have a max of 10,000. If we're willing to pay the price of having 1,000,000 entries, then at most we could have 1,000 people. And if we remember the searching algorithm, searching through 1,000 entries was happening on the order of a few hundredths of a second. All right, so that's a very, very high quality algorithm. So keys, not everything is an integer. They don't need to be. We know in a dictionary object we can use a key value of anything really. In Python, strings can be hashed to ASCII representations. Floats can be turned into integers. We can multiply by some number. Generally, objects can be assigned by either some simple property, but really what Python does is it uses the memory address of the object as the hash value. So that offers a pretty convenient integer basically to serve as the hash value. So it's not necessary for keys to be integers, and certainly we know that from our use with the dictionary. So there's a little bit more complicated transformation to turn the key into a hashed index, but it's the same concept. It's the same exact idea. So the dictionary is really just a hash table. Hashing is a really big complex topic in computer science. It's used beyond hash tables. It's also used in cryptography. It can become very, very complex, but and certainly that's not really what we're after in this type of a course. But what we've gone over just now in the last 15 minutes or so is enough for you to gain a little bit of an appreciation of why the dictionary would be very effective in certain cases. So a dictionary object, it allows very, very fast lookup and retrieval, and what you're potentially sacrificing is a little bit of memory space. There will be a little bit of overhead using dictionaries. But generally, in most situations, if you know that you're going to be constantly looking for particular items in a set, a dictionary offers even better performance than sort of a list with an automatic lookup like that. The dictionary object in Python is very well tuned. It does hash. It automatically sets appropriate hashing mechanisms. It'll resize its table based on the number of collisions that are occurring. So it does a very, very good job of sort of hitting the sweet spot between search time and memory usage, and you can grow to pretty much to rely on it pretty well in nearly almost every circumstance.